All right, perfect. It's 2 o'clock, you guys. I'm going to go ahead and get started. So collection data types, before I get too far into this, let me just say, if you attended Alan Smith's presentation earlier today, where he talked about sets and maps, there's a lot of overlap between what he talked about and what I'm talking about right now. So there are 2 excellent presentations going on at the same time. One of them is Hunter Smith's stuff about UI, and the other one is John from NI talking about measurement link. If you were, trying to decide which presentation you wanted to go to, and you've already seen Alan's stuff about maps, sets and maps, definitely go check one of those other ones out. There's quite a bit of overlap here, so just wanted to put that out there. It will not hurt my feelings if you guys decide to go check out one of those other presentations instead. But with that being said, I'm going to talk today about collection data types. So if you go into LabVIEW 2019 and later, you're going to see a collections palette in the main functions palette. And inside of that is sets and maps. And you will not see strings and arrays inside of that palette. And so when I was first putting this presentation together, I kind of wanted to start at the beginning. I wanted to talk about the different ways that you could sort of collect the same data type in LabVIEW. And these 4 data types were the ways to collect data: strings, arrays, sets, and maps. Well, I didn't want to use the term collection because, again, that's already been assigned to sets and maps. So I went and I talked to my colleague, Stephen Loftus-Mercer, who worked in LabVIEW R&D at the time. And I was like, hey, can you give me another word besides collection that refers to like a way to have an arbitrary number of like things in LabVIEW? So in other words, sets and maps, but also strings and arrays. And he's like, yeah, I got the perfect word for you. You should say amalgamations. I was like, no, that's a terrible word. I'm not going to use amalgamations. So he tried to give me a few other ideas, and I didn't like them. So I decided to use my authority as a longtime LabVIEW programmer to just co-opt the term collection for my own use in this presentation to refer to not only sets and maps, but also strings and arrays. So when you see that word, when you see me use it, I use it a little bit more broadly than LabVIEW uses it. So yeah, before I get too far into this stuff, this presentation, I've given this presentation before. I gave it back in April. I did an internal training at NI, and this was the material. And as I like to do with all my presentations, this content is already available for you to download. Every one of my big presentations that I give, that people ask me to give, is listed at dnat.org. So you can go there, you can get this presentation and a bunch of other ones. I've already got slides, demos, and video recordings all posted there. And another thing before we get started, there's a lot of stuff in this presentation that's kind of fun to play along with. Like you can legit, like while I'm talking about this stuff, open up your block diagram and just kind of play around with it. I highly encourage that, particularly if you have multiple screens and it's kind of easy to do, right? When you've got the slides on one screen, then you can play with LabVIEW in another. So in fact, y'all might see me glancing upwards. That's because that's where I've got the chat where I can take a look at y'all's stuff. So anyway, but yeah, if you can, launch LabVIEW and play along if you have LabVIEW 2019 or later. Because there's a lot of neat stuff in here that's fun to just sort of experiment with on the LabVIEW block diagram. So in terms of how I view collections of things in LabVIEW, we're going to start with the most basic type of collection, which is a string. All right. So everybody knows about strings in LabVIEW. It's one of the first things that you learn. And if you stop and think about it, a string in LabVIEW is really a collection of characters. That's all it is. And if we're getting more specific, we could say that a string is a collection of bytes. And we know this because we've got functions like the one you see in the slide, string to byte array, where you can take a string and literally just convert it into an array of U8 values. Now you can see that's what I've done on this very simple VI. And you can see that we took the string dnat and we turned it into an array of characters where each element in the array is one of the characters in the string, D, N, A, T, T. And then just to be tricky, I also had a space that you can't even see in that string right after dnat. And then we can see that character as well. So yeah, there's these functions in LabVIEW that will turn a string into an array of bytes. And then that's the one you see in the slide. Then we've got the opposite function, which will turn an array of bytes into a string. Now, what the heck is up with these numbers? Like, why is D 68? Why is N 78? Why is a space character 32? Where the heck are these numbers coming from? Well, these numbers are coming from an ASCII table. Do you guys know what ASCII stands for? I didn't. I had to look it up because I've just only ever seen it as the acronym. ASCII stands for American Standard Code for Information Interchange. Now that I've said it, you don't ever need to hear it anymore because people are just going to use the term ASCII. So if you remember in the previous slide when I converted DNAT into an array of bytes, capital D was 68. And if you look in that table on the right-hand side of these slides, you will see a capital D is the number 68. So this is just a conversion between, standard characters like alphabet, number, punctuation into a numerical form, and that's what string to byte array does in LabVIEW. Now notice that this table of ASCII characters has 128 characters. We are going to come back and visit that in just a minute. So how do you know, or how do you kind of understand a mapping between these characters and the ASCII table? Well, there's a tool in Windows called the character map that lets you do this. So let's actually play with the character map a little bit. So you can just type in character map in your Windows search, and it brings up this app. And you can see that you can take, here, we'll use some characters that I don't normally type, like maybe an E with an accent mark on it, and an I with a couple dots over it. And we can copy those. And then if we, let's say, go into a LabVIEW front panel, then from the character map, we can just like paste them into like a string. And there we go. So that character map allows us easy access to those types of characters. So getting back to the slides, let's talk a little bit about encoding. All right. So we're talking about ASCII. Again, we don't really care what the acronym stands for. But you'll remember I pointed out that ASCII table we looked at had 128 characters in it. Well, that just so happens to be 2 to the 7th power. Well, that is 7 bits. And this whole time we've been talking about bytes, right? We've been talking about 8 bits. So the ASCII table showed all of the normal English characters, A through Z, capital, lowercase, punctuation marks, had a bunch of crap in there we don't use anymore, those non-printable characters. Well, the cool thing is we can use that 8th bit to give us more characters, like the ones that I just copied from the character map. Well, here's where things get a little bit weird. So if I go back to LabVIEW and the character map, so you'll notice that starting at the top, we've got all of these things that you can type with your keyboard, right? All of these things that are part of the English language. But then we start to get into things like a cent symbol and a degree symbol and a copyright symbol. Okay, that's okay. And other languages are going to have like an E with an accent or an A with an accent. That's fine. Well, you'll notice that there's a lot of stuff in this list. You can just keep going on forever and ever and see all sorts of characters, right? Well, remember a character in LabVIEW is 8 bits. It's a U8. We just talked about converting string to array of bytes, byte array to string. Well, if we look in this table, we can see that when we click on a given character, we can see what bytes it's using. And we can see that, for example, capital D, we talked about that before. Remember that was 68 in the ASCII table? Well, 44 in hex is 68. So, okay, that makes sense. That's how we're getting our mapping. Well, what happens if we go past that 8 bits, right? Like this is clearly more than 256 characters, right? So let's look at this Y with 2 dots on the top, all right? We can see that its code is FF. Well, that's the biggest byte that we can have, right? So let's put this Y with 2 dots in our characters to copy. And then right next to it in the character map is an A with a line over it. I'm sorry, I am a dumb Texan. I do not know what the right terms are for these things with the dots and the lines, so I'm just going to call them like I see them. I'm going to take this A with a line on the top of it and put it there. And we can see that it takes up 2 bytes. Byte number 1 is 01. Byte number 2 is 00. What happens when I put that in LabVIEW? This is what happens. The Y with the 2 dots got copied over just fine. And the question mark is there instead of the A with a line. And the reason is because LabVIEW can only display single byte characters on its front panel. A little more specifically, LabVIEW English can only display single byte characters on its front panel. If you're using LabVIEW for Japanese or Korean or Chinese, those can display multi-byte characters, basically characters that require more than 1 byte to display. LabVIEW for English does not officially support any of this. There is a way to get it to sort of work. I'm not going to talk about that in the presentation. You can go Google it if you want to figure it out. But for all intents and purposes, since I work in the tech support organization, I'm going to tell you that no, it is not supported. LabVIEW English can only display single byte characters. Now, LabVIEW R&D is definitely looking into ways to improve this in the future, possibly adding UTF-8 support in LabVIEW for English. It doesn't have it right now. But I wanted to just mention this stuff because if I'm talking about strings and LabVIEW, I kind of need to go into all of this because eventually you're going to run into a situation where you've got some text that's maybe in Japanese in Notepad++, and you copy it and you try to paste it in LabVIEW and you see a bunch of question marks. I wanted to explain why you see that, okay? It's because LabVIEW for English only supports single byte characters on the front panel on the block diagram. It unofficially supports Unicode. You can go Google and find out how to do that. All right, but for the purposes of the rest of this presentation, just going to be talking about regular old single byte strings. So why do we use strings in LabVIEW? The most common reason we use strings is because we need a collection of characters in our VIs, a collection of letters and numbers, something that we might possibly need to match patterns on. You can see in the slide, I have a pattern that will detect a number that's in a string. So like a negative number or a decimal number or whatever, that pattern that you see on the slide there can detect that in a string. Why do we need to detect that? Well, because that's kind of a human readable piece of information. Like if you see a string and it's got a number in it, you as a human being can recognize, oh, that's a number. If you have a string that has words in it, you recognize those as words. So typically we use a string as a collection of characters. Not as typically, we use a string as a collection of bytes. So why might we do this? So there are times where we actually do have human readable strings, but we want to turn them into arrays of bytes for performance reasons. A lot of the array functions are able to manipulate an array of bytes more efficiently than the string functions can manipulate a collection of characters. You can also operate on arrays in place. So you can use the in place element structure to go in and operate on elements of the array without having to worry about making new copies of the array. I'm not going to discuss in placeness in this presentation. I actually will discuss it in my 8 o'clock this evening presentation. Sorry, 8 o'clock my time, Central Time. When I talk about ludicrous ways to fix broken LabVIEW code, I'm going to talk about in placeness a little bit more in there. But really what you should do is just check out that LabVIEW compiler under the hood presentation if you need to learn something more about in placeness. And another kind of silly reason we have to use strings in LabVIEW is when an API forces you to use strings. And the perfect illustration of this is the TCP API in LabVIEW. When you do a TCP read in LabVIEW, you get back a string. It's almost never a collection of human readable characters, right? It's almost always a collection of bytes. Really, TCP read should probably be giving back us an array of bytes instead of a string. But here we are. It gives us a string. We usually probably convert it to an array of bytes and then figure out from there. So those are the reasons that you might want to use strings. So we've got some, if you want to kind of learn more about all these little idiosyncrasies, I know we don't really think about strings much, right? We kind of, it's kind of taken for granted, but there's actually quite a few interesting things about strings that are illustrated in the shipping examples. One of the things is 2 slides ago when I had that match pattern that gives you back any number that's in a string. That is a super useful pattern. I've copied it out of one of our shipping examples more times than I'd like to admit. So there's some nifty stuff in those shipping examples, just like code snippets and stuff that you might be able to utilize for dealing with strings. So I'm just going to glance at the chat real quick just to see if anything is jumping out at me. Neil is wondering why I didn't include cluster. I think in terms of this presentation, collections would be, a collection of an arbitrary number of things of the same type. So strings, arrays, sets, and maps can all have an arbitrary number of their element type. A cluster cannot. It's statically defined. That's why I didn't include clusters in this presentation. Let's see. Anything else? Commentary on the U.S. educational system. I agree 100%. Let's move on. All right. So let's talk about arrays. So we talked about a collection of characters before in a string. Now we're talking about a collection of pretty much anything. So an array can contain multiple elements of a data type and multiple dimensions. The array can have any element type except for another array. And we can see in the slides, I've shown a few illustrations of, an array of numerics, an array of clusters, etc. Now, anytime this topic comes up with sort of newer LabVIEW programmers, people that are learning LabVIEW for the first time, you introduce them to arrays, and inevitably they say, well, why can't I have an array of arrays? I've heard that so many times. I could have an array of anything. Oh, not anything. It's that one thing. Why? Okay, fine. When they first made LabVIEW a jillion years ago, they just didn't allow you to have arrays of arrays, and they never went back and changed it. That's why you can't have an array of arrays. So one thing that I find interesting is that there's a surprising number of LabVIEW programmers that don't know this trick, which is effectively a way to make an array of arrays. It's, if you've ever heard the term jagged array, that's what this is. And instead of trying to make, as we can see in the slide, instead of trying to make an array of numerics, you just have to make an array of a cluster of an array of numerics. You just throw that extra cluster barrier in there, and that's what allows you to effectively hack your way into having an array of arrays. So if you've never seen this trick, I utilize this trick pretty regularly, maybe less regularly now that I have sets and maps, which we'll obviously visit in this presentation, but it's still a pretty common pattern that you might see. All right, so arrays. Another thing that can really bite us with arrays is the fact that they're zero indexed. I recently was working on a project with a pretty big LabVIEW development team, and one of the pieces of hardware that they were interfacing with had channels 1 through 24. So everything in their documentation referred to channels 1 through 24. Everything in the user interface for the testing framework that used this hardware had listed channels 1 through 24. And of course, the channels were being dealt with as an array of 24 values. So anywhere in the UI where we said pick your channel number, we had to have a place in the code where we decremented whatever you picked, because everything in the array itself is zero indexed. And then anytime we had to pull out a value from the array and let you know which channel had a problem, we had to go make sure to add 1, so that we were telling you in the UI, hey, channel 8 has a problem because index 7 in the array had a problem. Super frustrating, but definitely something we need to keep an eye on, or keep, be paying attention to. In my opinion, everything in LabVIEW when dealing with arrays should be zero index. Like from day one, this customer should have referred to everything as channels 0 through 23. That would have made our lives a lot easier, but alas, they did not. So this is definitely something we have to keep in mind when dealing with arrays. But yeah, there's a jillion functions in LabVIEW that let you, do stuff with arrays. Arrays have been around in LabVIEW for so long that, if we really think about how our compiled code gets executed, there's a lot of optimizations in the LabVIEW compiler that deal with arrays. Like if you've got a build array function inside of a loop and that loop runs a million times, the array is not being reallocated a million times. There's like heuristics and cool things in the LabVIEW compiler that figure out, based on the way your diagram is constructed, let's allocate 100 items when we do this build instead of just 1, because chances are the next 99 iterations of this loop are also going to I'm oversimplifying here, but the point is there are a lot of optimizations in the LabVIEW compiler associated with arrays. So, and those of us who've been programming in LabVIEW for a while, we tend to find these patterns, like using the in-place in-place element structure. Other things like, we happen to know that if you branch a wire just to get the size of the array, that's not going to make a copy. And there's a lot of other things that don't make a copy. So yeah, a very rich API around arrays in LabVIEW. Now I'd like to talk about the matrix data type. Have you even heard of the matrix data type? If you go into LabVIEW in QuickDrop and type in matrix right now, you'll see a bunch of functions come up that deal with matrices. And if you drop one of those functions and create controls and indicators off of their matrix terminals, you will get matrix data types. You will not get a 2D array of doubles. But here's the thing. A matrix and a 2D array of doubles are exactly the same thing in LabVIEW. The only difference is that the matrix is a type def, and when the LabVIEW editor sees that type def anywhere in your VIs, it draws the wires funny. That's the only difference. If you've got one of the matrix VIs and you wire in a 2D array to it, it's going to work fine. If you've got a VI, an analysis VI that takes in a 2D array of doubles and you wire in a matrix, that's going to work fine. The matrix is literally just drawn different. In my opinion, it's kind of an overcomplication in LabVIEW. I don't think that this data type should have been introduced as a new data type. I think, we should have just stuck with 2D arrays of doubles everywhere, but I didn't make the decisions. So, but yeah, you can see in the slide even, you can just see that the matrix just has the type def symbol on it. It's just a type def of a 2D array of doubles. There's also a complex matrix you can have that are, complex doubles instead of regular doubles. But anyway, yeah, so I just wanted to mention, if you ever see the matrix data type and you wonder what the heck is that, it's a 2D array of doubles. That's really all you need to know. So I decided I wanted to include a few tricks in this presentation with arrays. These are just little things I've come across over 2 decades of LabVIEW programming that may be obvious to you, may not be obvious to you. The first one there is that if you ever want the last element out of an array, that's the easiest way to do it. You call delete from array. You don't even wire the array output. You're not even using the array that had the thing deleted. You just get the last element. By default, delete from array is going to return the last element in the array to you. And so that's just like this, instead of having to like array size -1, index array, I mean, that'll work. That'll give you the last element, but just delete from array, much easier way to grab the last element. Now, right below that, we have the matrix size function. So I just talked about matrices. You might think by its name that the matrix size function only lets you wire in a matrix, but that's not true. You can wire any 2D array, a 2D array of strings, a 2D array of clusters, a 2D array of whatever, into matrix size, and it will give you the number of rows and number of columns. So that's super convenient. Question that I'm glancing up and seeing Josh is asking if delete from array causes a data copy of the array. It does not. So it definitely does not in the picture that you see on the slide, because we don't even use the array output. So the delete from array function, the LabVIEW compiler optimizations are basically like, we just need to allocate a spot in memory for this element that we are giving you from the array. Interestingly, delete from array where you wire the array out also doesn't necessarily make a copy of the array. If LabVIEW figures out that it can reuse that array input for the array output, it will not necessarily make a copy. Now, there's sometimes where LabVIEW cannot reuse the array, and that's when you get into things like the show buffer tool that can kind of give you an illustration of maybe this is going to allocate a buffer, maybe this isn't. But yeah, I think so just to take an aside here really quick, the question of will LabVIEW make a copy of this wire right here when I do this thing to it? That is a question that is extremely difficult to answer and almost always has to be looked at on a case-by-case basis. And because of that, a lot of LabVIEW programmers have in their heads that if I do a thing on this wire, or if I do a thing with, if I call a function on this wire, or if I branch this wire, LabVIEW is going to make a copy. And I think the reason that we've all kind of fallen into that view is just because the real answer is so complicated that the easy answer of, oh yeah, it's going to make a copy is much easier to fall back on. But the real answer is that the LabVIEW compiler has so many freaking optimizations in it that a lot of the times the answer is no, LabVIEW will not make a copy. But those times are really difficult to identify other than looking at a case-by-case basis. So sorry, I just wanted to give an aside there for a minute. Anytime somebody says, oh, that's going to make a copy, it might not. We need to know just by looking at that situation. But I can tell you for sure, looking at the picture on my slide of delete from array, there definitely is not a copy of the input array if all you're doing is looking at the last element and not even using the array output. So clear as mud. So in the upper right corner of the slide is an illustration of a way to get around a pet peeve of mine, which is when I see people write LabVIEW code that they wire every single input on the index array function. It makes for a crowded block diagram of constants and wires flying around when a lot of them really aren't necessary. So if you do not wire the index input on index array, it's just going to give you back the next index that it otherwise would have given you. And just to illustrate that, just look at the picture. If you don't wire the very first index, you'll get element 0. If you don't wire the next one, you'll get element 1. Oh, look, we wired a 5 into the next one. So let's give us back element 5. Oh, and we didn't wire anything into the next one? Okay, well, let's give us element 6. That's the next one after 5. You see how this can make your wiring a lot simpler if you just kind of use the assumed indices instead of having to wire every single one. I'd like for this to become a more well-known thing, because I see index array with just so many wires hanging off the left side of it that don't necessarily need to be there. Okay, so in the middle of the slide, we've got these malleable VIs. So NI has taken this convention of like this sort of light peach colored orange on the backgrounds of malleable VIs that we ship with LabVIEW. And there's a bunch of those related to array functionality. So if you open a recent LabVIEW and look in the array palette, you're going to see several malleable VIs with those peach colored backgrounds. Some more useful than others, to be perfectly honest. The one on the bottom there, remove duplicates from 1D array. Oh my gosh, I use that thing all the time. I love that malleable VI. So you're going to hear me presenting later this evening on ludicrous ways to fix broken LabVIEW code. And one of the things I talk about in that presentation are problematic malleable VIs. I do not consider remove duplicates from 1D array a problematic malleable VI. If you look at its block diagram, which apparently Kevin has already done according to the chat, it's a really simple malleable VI. And my rule of thumb for malleables is, as long as they're simple, I'm doing that in quotes, I'm okay using them. And some of these are examples of simple malleable VIs. And then in the bottom right corner, we've got in-place element structure, just a way to operate on arrays efficiently. Most of you guys know about that. One thing you may not know is that there is a VI analyzer test called in-place element structure usage that will scan your diagrams and detect patterns where you are not using in-place element structure, but you probably could be to improve your code's efficiency. So check out that VI analyzer test if you have not seen that before. All right, let's see. I think that's mainly what I wanted to talk about arrays. We've got some shipping examples there. Let me just glance at the chat real quick and see if I missed anything. Yes, Christian, I agree with you. I wish the in-place element structure did the same unwired index smart behavior that the index array function does. Unfortunately, it doesn't. So you have to wire those indices on the in-place element structure. Piotr's talking about how in one version of LabVIEW, you might get a copy made under certain circumstances of wire branching or function calling, and in another LabVIEW you may not. That's exactly right. In fact, if I go back to my previous slide, the delete from array trick that I show in the upper left there, I demoed that at an NI week like 10 years ago. And there was somebody from LabVIEW R&D who was attending my presentation who said, oh crap, that's making a copy and it probably shouldn't. And he went and fixed the compiler to no longer make a copy. So you're right. As LabVIEW releases come out, there are improvements made to the compiler and optimizations that are made that give us some of this cool behavior that we didn't have in older LabVIEW versions. All right, so yeah. So all that being said about arrays. Arrays are really useful in LabVIEW. We use them all the time. Why do we use them all the time? Because of the use cases that they facilitate. If we look at that very simple block diagram snippet, if I have a list box on my front panel where you're picking something in a list and there's data associated with your selection, I'm probably keeping that data in an array. My list box has items 0 through 9, and you pick item 4. I'm indexing item 4 out of an array to give you the data that's pertinent to that selection you made. It's almost like a really simple key value pair where the key is an index into the array. Now, there are some things we have to consider when we're using arrays. You can have duplicates in an array. Maybe that's good, maybe that's bad. You don't have to keep the array sorted if you don't want to. In fact, I would venture to say most of the arrays that we work with are not sorted. There's a lot of APIs in LabVIEW that require arrays just because that's how they were written. Like all the VIs in the analysis libraries, those all use you're calculating an FFT, you're passing in a 1D array of numbers. Arrays give us the ability to have multiple dimensions. I would say maybe once every 5 years, I need a 3-dimensional array. But it's there if I need it. 2D arrays, obviously, we use a lot more often. And prior to LabVIEW 2019, arrays were kind of the only way we could collect data into the use cases that are described on this slide. But in LabVIEW 2019 and later, we got a new data type in LabVIEW called the set. So this is a set. So if we look at the slide, I'm going to zoom in here, and we're going to see that we've got this set constant here. So this is a constant of data type set. We've got this funny looking wire here, which kind of looks like a spotted snake, and that is the set data type. The color of the set wire is going to change based on the data type of the set inside the set. The set element is a double number, which means we're going to get the double color on our set wire. And then we've got a set indicator on our front panel as well. So if we look at this code, it kind of seems similar to an array, right? It's a single data type. So in our example here, we've got a set of doubles, kind of like you could have an array of doubles. We can see that that set can hold an arbitrary number of elements, just like an array can hold an arbitrary number of elements. But let's look at the differences. There is no concept of an index in a set, and this took me a while to wrap my head around. If you look at that picture of the set on the far right, the set indicator on the front panel, you see it's got 4 values in it, values 1, 2, 3, 4. Why can't I just pull out the value at index 2? Sorry, doesn't work that way. That is not a concept of sets. Even though it looks just like an array where you could do that, you cannot do that. Also, you can see the set does not have duplicates. So we tried to add in all of those array elements to our set, pictured on the left there, 3, 1, 2, 4, 4, 3. But we can see the duplicates did not show up in the list. We can also see that the set data is sorted. Now, if you've worked with sets in some other languages, and I have not because I only know LabVIEW, but it's my understanding that other languages don't necessarily have require the sets to be sorted, but LabVIEW does. Also, one other difference from 1D arrays is that a set can contain any data type. Now, which data type can an array not hold? An array cannot have arrays. Well, a set can have sets. I have never needed this. I'm sure somebody's needed it, but you can see here we're building a set, and then we're building a set of sets, and there's no problem. Like when I say a set can contain any data type, I literally mean any data type. Anything, any data type you can think of in LabVIEW, you can make a set of it. So this diagram illustrates some of the most common functions you are going to use with sets. Now we can see on the far left, the first thing we do is we have an array of numbers, and with the for loop, we're going to insert those numbers one at a time into the set using the insert into set function. Then we've got a function that gives us the size of our set. That's called collection size. Next, we can check to see if an element is in our set. On the slide, we can see here, we're checking to see if the number 4 is in our set. And then we can remove things from our set. And then one of the nifty things in the language is that if you want to turn your set into an array, all you have to do is wire it to the border of a for loop. And then that for loop is going to iterate on the elements of that set. So let me show let me do a little bit of a demo. I'm going to do some live coding here. So get your popcorn ready for when I screw something up. So what we're going to do is we're going to write a spell checker, but we're going to use a set to do it. So in order to write a spell checker, the first thing that we need is a dictionary, right? So, and we're going to want to read that into LabVIEW. So the first thing I'm going to do is get a dictionary. Now, I don't normally like to do path browsing during demos, but I'm going to do it now because it's a pretty nifty path. If you look in project VI analyzer tests documentation user, sorry, I don't have that copy pasted into the chat, but maybe somebody else can. You're going to find a file called standard-dictionary.txt. And so the VI analyzer ships with a spell check test. And part of that is an open source dictionary, and it's inside this text file. So if you ever need a list of 77,000 English words, that's where you go to get it. So next, once I have that, I need to turn that into an array first. So I'm going to turn the contents of that text file into an array. And I'm going to make sure that that array looks good. We're going to run the code. We're going to see that it goes from A to Zimmergy, so that sounds pretty good. And yeah, it was 75,000 something. Yep. All right, so let me turn that into a constant. That way we don't need to run this code that's looking on the disk every time. Okay, so now I've got an array constant that has a pretty substantially sized dictionary in it. And so what I need to do now is I need to change that into a set. So the way I'm going to do that is I'm going to drop this insert into set function, and then I'm going to, this is how I usually like to make my set constant that's empty. I like to do it this way as opposed to like dropping a set constant and then changing the data type into it. I like to do it the way I just did it there. And then let's make an indicator here and run it. And we can see up, there's our set with a bunch of items in it. Let's change that into a constant as well so we don't have to run that code every time. And so now we have a set constant that contains a dictionary. So now I'm ready to write some LabVIEW code that does some spell checking on a string. So let's say this string has no spelling errors. And let's make it bigger so everybody can see it good. And then what I need to do is I need to take that string and once again use my cool delimited string VI to turn it from a string of characters that are delimited by spaces into an array. And then inside of this for loop, I'm going to check and see if every one of the words in my string is an element of this set that I created. Again, sorry for the sloppy block diagram. And if the word is not in the set, then we're going to assume that it is a spelling error. So if not found, then it's a spelling error, and we can show that on the front panel. And if we run this code, we should see that there are no spelling errors. Oh, I forgot to turn my string lowercase. All the words in the dictionary are lowercase. Okay, no spelling errors. And now if I start typing some random characters in here, we will see that I've got my spelling errors. So, all right, what's the big deal about sets, right? Why did I just write this demo? Yeah, Piotr was on to me with the lowercase thing. So here's what the array code would look like. All right, so that's our array, and now everything's all jumbled up because I've been sloppy. And so now I'm going to write the same code. Let's see. We will check our words against the array, and we will build up an array of the spelling mistakes there. And we will, if it is not in the array, so less than 0, then that's going to build up those errors. We should see that the spelling mistakes returned by the array check are the same as the ones that returned by the set check. So that's good. So what's the deal? Why do we have sets? Why did I just write that code using sets instead of arrays? Both seem to work just fine. Well, the deal is this versus this. So when you are checking a set to see if an element is inside of it, it is much, much faster than when you are checking an array with search 1D array, because this is a linear search and checking a set is a much faster binary-ish search. So this is why you're probably using sets. You don't have duplicates and you want very fast lookups. Those are the main reasons. Jesper's asking if I'm using Zoomit. Yes, I'm using Zoomit. Norm and I are going to talk about Zoomit in our 4 o'clock presentation. Norm has converted me to a Zoomit guy. So that is why we like sets. Sets give us removal of duplicates and very fast lookups. Now, there's other stuff you can do with sets. You can manually construct a set on the block diagram with the build set function, kind of like build array. If you've got constant values or control values or whatever that you want to create a new array from, same thing with sets. And then the set functions also give us union and intersection and difference functionality. So it's very easy to, given 2 sets, find out how they overlap and how they're different. Carson asks, is there a function to get all elements of a set at once? I assume you mean to get all elements of a set as an array. And yes, the way you do that is shown there on the right side of this block diagram. You wire the set into the border of a for loop and build a new array. That is not an efficient operation, by the way. You need to really decide if it's worth your block diagram execution time to turn that set into an array. But that's how you do it, wire it up to a for loop. All right, so we have a shipping example for sets. I think it does some wordplay as well. You can check that out in the collections, the examples collections folder. Let me get some questions here. Let's see. VI Analyzer will complain about VI metrics when you have a 700K constant on the block diagram. Yeah, turn off that test in the VI analyzer if you don't like that result, I guess. Okay, I'm going to keep going. So to summarize what I just said before, if you're in LabVIEW 2019 or later, you've got sets. A lot of the things that you used to write with array code, like, oh, I need an array for this stuff. At this point in your LabVIEW adventure, you need to pause and think, wait, would this be better to do it with a set than an array? And a lot of times the answer is yes. Sometimes the answer is no. Like if you have index-based lookups, like I talked about before with like a list box-driven UI, that's just the simplest example I can think of. That's an index-based lookup. You definitely are going to want arrays there. But if you really need, like, you've got some tight loops that are doing fast queries, sets are going to give you a much quicker way to do queries on the set contents than doing a search on an array. But at the same time, remember what I said at the beginning. LabVIEW sorts data in a set. I actually don't know the reason why we do that. Maybe somebody does and can post it in the chat. But the fact that an insert on a set is always going to keep things sorted means that set inserts are kind of slow relative to something like build array, where you're just throwing things on the end of an array. I would venture to say LabVIEW can do that more efficiently than it can insert into a set. So if the slow inserts aren't a problem, then sets are another area you can look into. If you don't want duplicate elements in your collection, then sets are great because they automatically prevent you from throwing duplicates in there. And then a set is it's not going to be associated data. An array is associated data because you've got a value associated with an index. Whereas a set, there's no association. You've just got the sorted list. Gregory asks in the chat if the sorting helps the search speed. It probably does. I'm guessing that's one of the reasons that it does. And then finally, if you need random access to elements, sets are actually pretty terrible. And the reason is, you can see from this screenshot here. Let's say that we have an array of 1 million strings. It is going to take exactly the same amount of time to pull out the 0th element of that array as it is the 999,999th element from that array. Those two scenarios are going to take exactly the same amount of execution time. So the value generated by the random number is going to have no impact on our execution time. But if you look on the bottom, you can see that if you need a random element out of a set, this is the only way to do it, and it's terribly inefficient. We're basically going to generate the random number and iterate the for loop that many times until we pull out the item that you said you wanted. So if you want the 0th element out of your map, or I'm sorry, if the random number, and I guess I'll use 1 indices here because I've got the 1 there. If you say you want the first element out of the set, that for loop is going to run 1 time. And if you say you want the 1,000,000th item out of that set, the for loop is going to run 1,000,000 times before you get the random element. So I have run into exactly 1 situation where I needed a random element out of a set, and I was really kind of bummed out that I had to write the code that you see on the slide. That's the only way I could think to do it. That's the only way that some of my colleagues in R&D could think to do it. So if you need random array, or if you need random element access, you're probably better off with an array than a set. Let's see, looking at the chat, Christian, it only sorts for display. The internal data structure is fancier. Fancier is a good way to describe it. Do sets duplicate the data in memory like arrays do? I don't understand the question. What do you mean by duplicate the data? I talked earlier about when copies need to be made for things. You can, I guess we can fall back on that and say that, the LabVIEW compiler is going to decide sometimes it needs a copy of things and sometimes it doesn't need a copy of things. And then John is asking about variant attributes. I'm going to talk about variant attributes later on in the presentation. Okay, so we ready to talk about maps. So we just talked about sets. It's kind of like an array, but no duplicates and faster lookups. There, how's that? Maps are a key value pair. So whereas a set is just a collection of a single type of things, maps are a way to map a value to a key. Now, just like with sets where you can have a set of any data type, in your map, your key and your value can be any data type. And so to make this slide, I thought I'm going to think of a ridiculous, nonsensical key value pair that I could put in this slide to illustrate how you can make anything a key and anything a value. And so I decided to make a key value pair where the key is an array of complex doubles and the value is a pair. I'm sorry, the value is a path. Yeah, nobody's ever going to do this in real life, but it does kind of illustrate my point that you can do a lookup on any type of key and return any type of value. So in terms of common functions with maps, this diagram is going to look pretty similar to the set diagram. We have a function that lets us insert things into a map, but now instead of just inserting a single element into a set, we are inserting a pair into the map, where the pair is a key value pair. We have a way to get how many elements are in the map. We can look in a map to see if a thing is there, and if it is, get its value. We can remove things from maps. And then just like with the set, where you can index on a for loop to pull all the elements out, you can also index on a for loop to pull all the keys and values out of a map. But in order to do this, LabVIEW turns your map elements into a cluster where you can have the key and the value. And the last time I gave this presentation, Derek Bomarito made a very good point, which was if you label your elements in your map, which I did not do, you can see over there on the left, the string and the numeric that are inside the map don't have labels. If you do label those, then whenever you unbundle in a for loop, if you need to iterate on the map contents, you can unbundle by name. And so your code is going to be more descriptive instead of just using a regular unbundle function. And a couple of other things you can do with maps. Again, you can build a map from scratch on a block diagram with the build map function. And then the in-place element structure allows you to look up a value and operate that on that value in place. There are some shipping examples on maps that illustrate their functionality. Examples collections, that's the same place where the set example is. Now I've got some more things to say about maps. I've got some gotchas to share with you guys on maps. My first gotcha, which Piotr referred to in the chat, lovingly, I hope, or maybe not, I certainly don't love it, is the inverted logic on the found Boolean when you are searching a set versus when you are looking in a map. So on a set, if you look for an element, you get a Boolean that says, if it was found, you get a true. So obviously it stands to reason that if you do the same thing on a map, you definitely want it to give you back a false if it was found. I'm being ridiculous, but unfortunately the functions are not, because that is exactly how they work. I asked the author of these functions why he did it that way. After he explained it to me for about 5 minutes, he said, maybe that wasn't the best idea. But by that point, the feature had already been released, so we're pretty much stuck with it forever. But yeah, my trick for this is whenever I'm working with sets and maps and I need to know whether an element is in a set or in a map, I will hover over the Boolean terminal on the function to see if its name is found or if its name is key not found. And that reminds me whether or not I need to invert the logic on the function. Again, I apologize on behalf of LabVIEW R&D for this inverted logic. Another gotcha that I have run into is when you use references as map keys. This was a bug in LabVIEW that was fixed, where sometimes the reference, the key, you would expect a match, and a match was not given to you when a reference was referring to the same object but obtained in a different way. Think about VI references. You can call open VI reference. You can read the owning VI property of a control. You can read the all VIs and no, that gives you back strings. You can read the VI reference property of a project item in the project. There's a bunch of different ways to get a VI reference. Those VIs could be referring to the same VI, but the map lookup, if you were using these references as keys, would return that they were different objects. And this was a bug that was fixed. I'm still a little bit wary. I would prefer to write the code on the left than the code on the right. I would prefer to get something besides a reference and use that as my key. But I know other LabVIEW developers who prefer the code on the right is cleaner. You've got one less property node you have to deal with. But I'm still a little bit wary of using references as key types. So keep an eye out for that. And then another issue I have found, I'll point out that the version of LabVIEW that I use as my daily driver is 2020 SP1. There is definitely a performance issue if you start using retain wire values for debugging, and you've got set, in my case, it was a set with 100,000 elements. If I turned on retain wire values and tried to run my code just took forever. It was just taking, because I had retain wire values on. But identical code that used arrays instead of sets did not have that problem. So there was some sort of performance issue. I haven't tested in later LabVIEW versions. I probably need to file a bug on this, but that's something to keep in mind. If you're using retain wire values, you might run into some performance issues with when trying to debug set code. All right, so somebody in the chat asked earlier, I think it was John, about variant attributes. So what it's some of you in this meeting may not have heard about variant attributes. What the heck are those? Well, you've got the variant data type in LabVIEW, right? It's the purple wire. You can store anything inside of it. You can convert to and from variants. Well, there is a feature with variants where you can store something called variant attributes. And it's kind of a way to have metadata, like associated data with your variant. Like maybe your variant contains something in it, and maybe you want to just throw some metadata, some tags on alongside the variant that kind of describe, overall what's in this variant. What are we dealing with here? Well, people back in the LabVIEW 6.0 days discovered this feature, variant attributes, and started using it for a completely different purpose than what it was intended for. Which was they completely ignored the value of the variant. They were using an empty variant, and they were storing lookup data in the variant attributes. Why were they doing this? Because variant attributes are key value pairs, and lookups on those key value pairs are very efficient. LabVIEW uses, I think, a red-black tree as opposed to like a linear search you would get with an array for doing searches on variant attributes. And so people started realizing, whoa, I can get these really fast lookups in LabVIEW by storing all of my key value pairs as variant attributes. And so tons of people started doing this. So many people started doing this that LabVIEW R&D started paying attention, like in the LabVIEW 8.0 timeframe, and saying, hey, maybe we should make this stuff more efficient, because like people are using these as lookup tables. Why don't we make them as efficient as they can possibly be to be lookup tables? And so variant attributes became a very, very efficient API in LabVIEW for key value pairs, even though that's totally not what they were made for in the first place. Well, and that's what we've been using for many, many years. We've been using variant attributes for our key value pairs since LabVIEW 6.0. So what about today? Now we've got maps, right? Maps are the legit key value pair API in LabVIEW. Is there any reason I should keep using variant attributes? Well, if you're in LabVIEW 2018 or later, you don't have maps yet. So yeah, you're kind of stuck with variant attributes in 2018 or later. If you're in LabVIEW 2019 or later, I'm confident in suggesting using maps pretty much all the time. They're more performant in 99% of their use cases. Now, what about that other 1%? Well, here's the deal. Back between LabVIEW 8.0 and LabVIEW 2019, LabVIEW R&D spent a ton of effort optimizing variant attribute lookups just because of how many people were using them and as lookups. We wanted LabVIEW to be performant for you, and this was the API you chose, and so we were making it faster. Well, we made it so fast that there are very tiny scenarios where a variant attribute lookup might be slightly faster than a map lookup. Those are few and far between. And they also require the lookup key to be a string and a lookup value to be a variant, which is a pretty limited set of cases. So that's why I feel confident saying just use maps for your lookup tables in 2019 and later. You really don't need to use variant attributes anymore. I've got a couple minutes to show a really quick demo of performance related to maps and variant attributes and whatnot. To sort of illustrate why maps are such a better API at this point. So I'm going to open up my map demo project, and I'm going to show you a real world scenario that I was presented a few years back. So there's a team at NI who was doing data lookups. I think it might have been a team in DAC R&D. I forget where it was, but it was a peculiar lookup because their keys in their key value pairs were complex numbers and their values were integers. And so the code that they had was doing a search 1D array on the array of complex numbers, and getting out the index and using that to index into their value array. And they wanted to make this code faster. Their lookups right now are 700 milliseconds, or microseconds, sorry. So they had heard about variant attributes. They had not yet heard about maps. And so they thought, well, okay, let's use variant attributes. We've heard about these things. They have these really fast lookups, right? So what we're going to do is we are going to take the array. We're going to take a variant. Remember, it's an empty variant. We don't care what its value is. And we're going to set attributes of that variant to be the key and the value. Well, the problem with variant attributes is that the key has to be a string. There's no way around this. So they were flattening their complex number into a string and using that as the key, and then they've got the integer as the value. And then whenever they needed to actually do the lookups, they were flattening the complex number again to a string and then doing the lookup of the attribute. So they wrote this code, and then they got really upset because even though they had been told that lookups with variant attributes were way faster, they turned out to be way slower. And they asked me to take a look at the code and help them figure out why that was the case. And the first thing I said was, why aren't y'all using maps? And they said, we haven't heard of maps. So the second thing I did was, well, let's look at your code and figure out why. And it's actually pretty obvious why. Flattening to string is extremely slow. This is killing any lookup performance they might be getting from this. So that's why things are taking so long. They can't use a complex number as their key. So they flatten it to a string, but the flattening is just killing any performance gains the lookups might have been given. So that's when I said, let's look at maps, because in maps, there's no conversion necessary. We can make our key be the complex number, and we, whoops, I am not a Zoom expert like Norm. We can make the key a complex number, and we can make the value an integer, and there's no conversion required, no flattening or anything. And so whenever we do our lookups, we just straight up wire in the complex number and get the value out. No conversions needed. Christian's asking if typecast would be faster. No, typecast is also very slow for things like this. Maybe it is faster, but it's still really slow. So anyway, we switched over to maps. We ran the code, and we discovered that the lookup time was incredibly fast because at this point, LabVIEW is storing all the keys and values as their native data types, no conversions necessary. And of course, the lookup with a map is going to be way faster than the lookup with a search1D array. So if we switch back to the slides here, we have a summary, and we're finishing just in time here. So in terms of the collection data types in LabVIEW, you're going to use a string if you need to do any pattern matching or if you have any human readable data, or honestly, if you're stuck with strings like with TCP read, for example, it doesn't give you any other options. You're going to use arrays whenever you need index-based data, whenever you're using existing APIs that make heavy use of arrays like the math analysis libraries. Sets are a new type in 2019 and later. They are ordered, they prevent duplicates, and they have very fast lookups. So if you're finding cases where those are those are the requirements, then a set is the way to go, not an array. Similarly, if you need key value pair lookups, we now have maps in LabVIEW 2019 and later. We can do key value pair lookups, fast lookups, no data conversion required like with older APIs like variant attribute tables. All right, you guys, that is all the material I had. I have a couple minutes to answer any of the questions in the chat. Remember, this presentation and all my other presentations are available at dnat.org. So any final questions before we wrap this thing up? Thanks, by the way, everybody, for participating in the chat. If y'all saw me glancing upward, it's because the chat I have on my other monitor up here, I'm keeping an eye on while I'm presenting. Any final questions, last minute comments, anything like that? I finished us just in time to make it to the next presentation.